for joining in today. My name is Angela, and I am the marketing manager here with Streetwave. We have Tassos from RF Elements with us today who will be doing the presentation. I would just like to ask if you have any questions, please go ahead and type them in the questions box, and we will get to them at the end of the presentation. I will now go ahead and pass the mic over to Tassos to take it away.
Good morning, everybody, and thank you for joining. Today we'll be going over our Increasing Throughput 101 webinar, our technology for fast, sustainable wireless, and some techniques and some information on how our antenna technology can help you increase your throughput and overcome some of the obstacles you're dealing with now in delivering more throughput to your current users. So the challenge that we have is basically the growing demand for throughput. If we look at the number of users that are requiring broadband internet, we can see it growing constantly year over year. The other challenge, along with the number of users, which is in the billions, the demand for the amount of throughput per user is also growing rapidly year over year. And we can see in 2016, on average, the average user speed is about 6.2 meg per user or above, with currently close to 3.4 billion people on the planet requiring high-speed internet. So the main challenge of the already challenge of delivering fast internet is the lack of spectrum. So the lack of spectrum could be looked in two ways, right? So we're kind of lucky here in the U.S. We have a pretty large amount of spectrum available in the 5 gig, but in a lot of countries the 5 gig spectrum isn't fully open to us. So if we look at the lack of spectrum, it could be the usable frequencies that we're allowed to use, but then when you compound on top of that the inefficiency of that spectrum due to noise and interference, it really reduces the amount of usable spectrum that we have. And basically the challenge that we are seeing is basically the growing demand of delivering this type of throughput, and vendors today are dealing with this growing demand by implementing new standards and that introduce higher theoretical speeds with more complex modulation, and all these new techniques require even more spectrum. So basically the spectrum that we have right now is limited to a high amount of RF noise. Wireless vendors today are bringing really advanced technologies and complex solutions like GPS synchronization to help you utilize channels more efficiently by reusing channels on towers. TDMA is another standard and complex technique that vendors are incorporating into their radios and actually treating them in a proprietary manner, not a standard, which makes you fixed to a specific vendor as far as your radio option goes. Active filtering is yet another technique or hardware addition to radio systems today that are used to work in this high RF interference world that we live in today for outdoor wireless. But this helps, or this adds cost and complexity to the radios that you're using. So all these techniques are used to address the issue, but none of these techniques are really sufficient because they're not dealing with the core of the issue. And the core is RF noise. So vendors today are not solving the problem at its roots. They rather deal with the consequences, and this is absolutely the wrong approach. You need to deal with the problem at the source, not employ all these other techniques that help compound the issue or work around what's really there, and that's inefficient antenna technology that helps add to the noise floor rather than reduce it. So if we look at some of the sources of these interference issues, it's really poor solutions that vendors are putting out, like shielding technology. Now this may help with co-location and some issues, but it's really not helping you from a throughput standpoint because it's warping your RF signal. It's making it more unbalanced out in the field to where your CPEs are, and therefore you're not able to maximize the throughput because it's a very poor designed or poorly deployed RF signal in the end. And this shielding is happening on not just point-to-multipoint devices, but also point-to-point, and it's gone as far now as to put shielding on even CPE devices. And quite frankly, you're better off using antennas that are clean and don't have these issues rather than add to the complexity of your install and the cost of your installs to deal with these issues. So if we look at from the radio standpoint, we can see the growing complexity of these radios. In the early days, all the enclosures were plastic, right? So these radios were leaking a lot of noise through the enclosure. As time went on, GPS synchronization comes to the table, again adding another layer of complexity and cost to your solution. And again, all of this is being done to deal with the problems of the antennas and inefficient spectrum usage rather than try and fix it from the get-go. And after that, you see GPS synchronization and active filtering and higher, more complex modulation schemes like 802.11ac using wider channels and higher QAM rates. All these things are, very complex problems to solve. So the RF element solution is simple, right? Deal with the source of the problem, and we do that through antennas that reject noise, have no side lobes. They don't accept the noise that's out there, so it helps you operate better, and also doesn't create more noise for you to deal with later. Also, RF Elements has zero loss solutions. Through our twist port technology, we're able to also reduce the loss that's in traditional antenna systems or outdoor radio systems today by removing the pigtail, which is a #1 failure rate for most outdoor systems due to water ingress, and then some signal loss as well. So again, dealing with the source of the problems are our horn antennas, which again have no side lobes, or a twist port technology which helps reduce loss. So the first key point in noise rejection, if we look at traditional sectors, traditional sectors have huge side lobes, they're very complex, and they're very high gain. So not only do they accept noise from areas outside of your coverage area, but they also send a lot of signal in the opposite direction or in directions that are not really needed. So all this starts adding to the noise floor and making it harder for you to not just co-locate on your existing tower, but also to work with other towers that are in your service area. If we look at symmetrical horn antennas, we see that there's no side lobes. You have nothing but main beam connectivity, and with very precise radiation angles, you're able to send your signal exactly where you want it and not send unintended signals in opposite directions. In the case of point-to-multipoint, the same thing applies. Actually, the higher you go in gain, the higher and more intense your side lobes are. So point-to-point antennas are actually a growing source of the noise floor. Most of these unlicensed point-to-point devices are mounted on your point-to-multipoint towers, right? This is how you get your bandwidth into your towers to deliver to your customers. So point-to-point antenna technology today is insufficient, and it's one of the biggest causes for RF noise. If we look at, again, using our horn technology for point-to-point, again, you can see very precise radiation angles and absolutely zero side lobes. So they're way more efficient in how they deliver the signal to the end user, and extremely efficient in rejecting the noise that's out there. So it helps you to coexist with the noise floor as it is. And as you build your deployments with horn antennas, you're also helping the spectrum start to clean up. So as you transition from the traditional sectors that are out there today to horn technology, you're doing yourself a favor, and you're helping yourself be way more efficient with spectrum, and also not adding to the noise floor, which is ever growing. Sorry, slides here. 1 second. There we go. So again, our zero loss system, if you look at a traditional system, you have a pigtail interface that connects the radio to an antenna. So we're able to remove that, incorporate a waveguide feed right onto a PCB, and therefore eliminate all the loss that's related to the current outdoor wireless solutions. And this, in a sense, helps many things. It's not just the failure rate of water ingress on pigtails or damaged pigtails, but it's also the signal loss and VSWR changes that could be induced into your system when you have pigtails. One of the other issues is these higher modulation rates that radio manufacturers are capable of doing today are no longer capable of transmitting on high output power levels, right? So in order to, let's say, do 256 QAM, your radio can only be set to, let's say, maybe 20 dB of output. If you go to 21 or 22 dB of TX power on your radio, you're unable to get those high modulation rates. And if you look at your EIRP limits, it's the gain of the antenna plus the output power. You would actually have to push more output power from your radio to make up for the potential loss or the loss of the pigtails, which might put you in that higher output power of the radio that does not allow you to hit 256 bit QAM. So with a zero loss system, with a twist port type radio system, you're able to reduce the power of your radio to maybe 18, 19, or 20 dB of TX power coupled with your antenna gain, and still meet your maximum EIRP limit. So it's a much more efficient way, and it's a way to ensure that you maximize the radio technology that vendors have employed to date. So let's do some comparisons about patch array antennas, your traditional sectors, and horn antennas. So if you look at a traditional sector antenna, you have your MIMO antennas, which have a horizontal and vertical beam. If you look at the overlay, the horizontal and vertical beam typically are not matched, so you get a coverage pattern mismatch where towards the edge of the sector, on the front of the sector, you don't have sufficient overlay. You also have noise that comes in through the large side lobes that are on the back of the antenna. And then as you get towards the edge, you have areas of low performance. Again, this is where gain starts to drop off. So if you look at your coverage area, you can see the center of your traditional sector antenna is kind of the sweet spot, right? That's the area where you'll probably get the best gain, the best vertical, horizontal, or chain 0, chain 1 performance, and therefore you'll get good signal and good speeds. And as you start going to the edge, the signal and the performance starts to decrease. With a horn antenna, you have perfectly overlapped horizontal and vertical beam patterns. Sorry, my animation stopped here. So you have nothing but main beam connectivity with constant gain and good signal. So all of your client connections are getting good modulation rates, stable modulation rates, and much better performance. So again, if you look at the overall performance of a traditional sector, you're getting some mixed speeds depending on where your client is within there. So if you average out those speeds from the good connections to the mediocre connections to the bad connections, the average speed that you're able to deliver through a traditional sector is greatly reduced compared to a horn antenna where everybody's got good chain-to-chain performance, and they've got good vertical and horizontal gain, and therefore the modulation rates are much more stable, and you're able to deliver higher speeds because you have a much better quality signal across all your customers. It's not something that changes depending on where your customer is within the beam. So let's look at noise rejection as you have a deployment on a tower. So if you have your access point and your client's obviously out in the field, with a traditional sector, you can get average throughput, usually not the amount of throughput that you would want to get or that the radio is capable of, because it's dealing with noise, and as you get to the edge of the sector, those modulation rates drop down. Because a horn antenna has no side lobes and perfect vertical horizontal beam performance, all your clients are in perfect signal areas, and therefore the link throughput or the overall throughput of that radio is maximized, right? You're not seeing again a decrease on customers that are far away, a decrease of customers that are in the outerlying edges of your sector, and you're not dealing with the performance hits of accepting noise. So again, the overall performance of using a symmetrical horn antenna definitely gives you much better average speeds across all your clients, and therefore a much better user experience. So let's look at the co-location issues that you have with traditional sectors and how symmetrical horn antennas can help you. So again, currently you deploy a traditional sector to cover the customers that you have. So again, you have kind of some average speeds because of the noise issue and where they are. And then all of a sudden you add more customers, and then your link performance drops even further, because radios are only capable of handling so many client connections. With symmetrical horn antennas, because we have narrow beam widths, you can actually deploy multiple access points with no co-location issues to cover the growing number of CPEs or customers in your coverage area, and all of them receiving good speeds across the board. So this is a great way to increase your throughput, is by using the ability of a horn antenna to co-locate multiple APs in the same coverage area and not overlap the whole beam. You're not taking 3 90-degree sectors and pointing them in the same 90-degree area. You can break that up into 3 30 degrees, or if you have a 120-degree sector, you can break it up into 2 60 degrees, so on and so forth. Because of the co-location capabilities of symmetrical horn antennas and the noise rejection, you get full speed on all of your APs in your coverage area, and therefore you get much better services to your customers. So again, if we look at the kind of old versus new, again, the traditional sector has problems because of the noise that it's able to accept through side lobes. You also have performance issues because the modulation rates and the link rates and the data rates that you get within your coverage area varies, where again you have kind of a sweet spot in the center, and as you start going to either edge of your coverage area, those speeds decrease because of chain mismatch errors and other things. And as your client density grows in that same coverage area, you don't have the ability with traditional sectors to go ahead and segment and break that area up and deploy multiple sectors. So clearly, 2 or 3 symmetrical horns would outperform 1, 2, or 3 traditional sectors trying to cover the same area. So I'd like to talk about channel availability. This is usually the #1 topic that comes up when we talk about horn antennas, and the efficiency of using horn antennas in specific areas. The one typical feedback that we get is, well, I just don't have enough channels to put up 3 horns. And actually you do. If we look again at how horn antennas work or traditional antennas work, you fire up your first AP, a traditional sector, let's say it's at 5700 megahertz, and then you have other sectors covering it. Because your traditional sector has such a wide angle and side lobes, it's actually hearing those other 2 sectors that you have in that area. Where if you put a horn antenna up, what you thought was a spectrum scan that didn't have available channels now are. So essentially, when you look at the available channels that you have in at your tower site, the reason you think you don't have channels is because you're looking through the eyes of your regular sector. Once you put up a horn antenna and you point in that same direction, you'll see that actual channels are available that weren't available before, because again, your traditional sectors are hearing so much signal coming from the back and the sides through side lobes and really wide radiation angles. So the precise angles of horn antennas filter all that out. So you actually have more channels than you think because of the noise rejection of a horn antenna. The same thing goes for noise floor, right? Noise floor is a huge thing. We're always looking for the SNR, right? We're always looking for how much more signal we can get above the noise floor in order to successfully get the higher modulation rates, right? You're usually looking for like 15 to 20, maybe 25 dB above the noise floor. Horn antennas also help with the noise floor. The same thing is employed here. So if you have your regular coverage area, noise might be coming in from towers that are further away, and because those towers are sending noise through side lobes, your noise floor starts to grow. In the same way, for co-location channel availability, the noise floor issue also goes away because horn antennas have no side lobes, and therefore the spectrum is way more usable than you think it is, because again, when you look at spectrum through a horn, it looks totally different, and it's way more efficient and allows you to reuse channels that you thought you didn't have available. So before you think, or before you say, hey, I have no channels, throw up a horn and have a look, and then you'll see exactly how many channels and what your spectrum could look like if all of your APs were on horn antennas. So massive scalability. This is really where we need to go. You saw earlier on how the number of users are growing globally, and the demand for throughput per user is growing. So in order to really cash in on this growth, you really need massive scalability. And traditional sectors today just don't give you the antenna technology that you're using with huge side lobes, high gain, is absolutely the wrong way to approach the need for massive scalability and increased throughput demand. You really need spectrum to be clean, or at least be able to cut through spectrum. So horn antennas give you that massive scalability. If we look at 3 potential sites, and you look at doing them with traditional sectors, again, you have medium to maybe some decent throughput, and as noise comes in, that overall throughput comes down. If you were to use horn antenna technology, your throughput goes up, and then we give you the ability of massive scalability to go ahead and segment those deployments up to multiple sectors, and therefore delivering way more throughput overall to all your customers with no noise and good noise rejection for any other sites that might be deploying it. So there's no other antenna technology on the market other than symmetrical horn antennas that will allow you to deploy the massive scalability that you need to match to meet the growing demand for throughput today. So our technology for fast, sustainable wireless, again, is using horn antennas. It's quite simple. We offer antennas in many different beam angles, everything from 30 degrees up to 90 degrees. So again, if your deployments are, if your customers are close into the tower, there's no need to use a 19, 20, 21, or even 22 dB sector to only go 1 or 2 miles, right? We have low gain antennas, wide angle antennas that are much better suited for those types of deployments. If you have a large number, a high density of customers in a specific area, stacking multiple traditional sectors not only takes up huge amounts of space on your tower, increasing wind loads, but it's inadequate for delivering the throughput that you need, where horn antennas solve that problem. Our twist port technology, again, allows you to really tap into our whole ecosystem. So as you grow and you change technologies, right, from 802.11n to potentially AC, our twist port ecosystem allows you to incorporate these new radios without having to change the antennas. It's somewhat, vendor neutral, and all this stuff gives you the massive scalability that you need for delivering, the throughput that's demanded today. So the key messages here, again, in increasing throughput with horn antennas is there's no need for GPS synchronization. So you can use any radio you want. It doesn't have to have GPS. No wide channels. There's no need to go to 40 or 80 megahertz wide channels. I mean, you could use much narrower channels. In fact, horn antennas are so effective at delivering quality signal and therefore maximizing your throughput and your radio connections. In many cases, you can deliver more throughput to your customers on a 20 megahertz channel on a horn than you were with a 40 megahertz channel on a traditional sector, because the traditional sectors are so inefficient at propagating that signal or a quality signal throughout your whole coverage area that a 20 megahertz channel will deliver, in most cases, more throughput than a 40 megahertz channel on a traditional sector. And again, there's no extra cost, right? So horn antennas are extremely cost efficient. There's no extra cost for buying shielding, aftermarket shielding, to put on these sectors to try and help with the noise issue. There's no need to spend tons of money on, these really complex radio systems that have TDMA, active filtering, and GPS and all this other stuff. You can get away with running lower end radios, lower cost radios that are on the market, and still deliver really good throughput to your end users without having to migrate to newer and newer platforms. So the cost efficiency is really good with horn antennas compared to traditional sectors. So we have a fairly active forum right now. So we ask you to join our community. It's rfelab.com. It's a great place for you to see what other people have been doing, the success stories that they have, and ask questions to either us or other users online on how they're deploying horn antennas, how it's helping them grow their business and deliver fast, sustainable wireless. And we also have a very active YouTube channels with lots of customer interviews, so you can hear from actual WISPs themselves, again, how they deployed our antennas, how they're using it effectively, and how they're growing their business based on our antenna technology. We're also available on practically every social media platform you can find. We have a YouTube channel, Facebook, Google+, LinkedIn, Twitter, you name it. There's many places in social media where you can reach out and interact with us, give us your feedback, ask us questions. If you need help with deployments, we're available on both the forum, via email, or on social media. So at this point, we've come to the end of the webinar, and I'd be happy to take questions if people have them. Angela?
Yes, there are some questions. So first question we have is, what is the availability of the PTP seed horns?
Sorry, the what?
The PTP horns.
Okay, so there's no firm ETA yet. They're still in development. We announced them or showed them at WISPAPalooza last year in Vegas. So there's no firm ETA yet, but it's in the works.
The next question we have is, are we going to see brackets for Air Fiber 5X?
Air Fiber 5X. So yeah, so we have a twist port adapter. Again, we announced that in Vegas at Wispapalooza. So yes, we have a twist port adapter for Air Fiber 5X. Absolutely. Again, there's no ETA, no firm ETA on delivery, but it's definitely something that's been developed and it's getting ready to come to market.
Okay, and then we have another question asking, are you going to have a slant 45 for Air Fiber 5?
No, no, we will not. You know, slant pole is is quite frankly something that manufacturers often bring to market. That really there's no huge benefit. I know there's a lot of back and forth and there's a lot of debate on whether or not it's really effective. To answer the question directly, as far as our Air Fiber 5X goes, it's going to be vertical and horizontal. So there's no plan to make a cross pole or a slant 45 at this time.
Okay. And another question, could you give more information regarding the connection to RF Elements equipment with end male connectors?
Mm-hmm. Yeah. So we have our twist port adapter line, right? So we have two types of horn antennas. We have our twist port horn, and the twist port horn is made specifically for our twist port ecosystem, right? So all the different adapters that we make that are twist port enabled or that take a small form factor radios that are on the market right now, like Ubiquiti Rockets, Cambian EP and P1000, Microtech router boards. We have adapters for them, and they all work with our twist port horn antennas. We also have our carrier class horn antenna line. Our carrier class horn antenna line is specifically made for larger form factor radios. So these carrier class horns have two end connectors on there, and they're made for, let's say, Mimosa A5C radios. They're made for Cambian, let's say PMP 450. Even the EPMP 2000 radio is quite large for a twist port. So basically, any radio that is connectorized that we do not have a twist port adapter for, you want to use the carrier class horn antennas for those, and you'll get the same exact performance.
Okay, we'll take a few more questions. There's one that is asking, what's a typical distance on a 90-degree antenna?
Yeah. So the typical distance is 2 to 3 miles. It's a short range antenna. It's I think 10.5 dB. So they go beyond. So we have like a we have spec ranges that we suggest that you stay within. Now these spec ranges by no means mean it's the maximum distance. The idea of the horn antennas is delivering high throughput to all your users. So in the case of a 90-degree, we say 2 to 3 miles if you're using something like a 21 dB antenna, so something like a Power Beam 300 or the old Power Bridge 21. So if you look at that smaller form factor radio, that's the distance you can see. And at 2 to 3 miles, you should get somewhere in the low -60 range, right? So you can clearly go beyond 2 to 3 miles to probably 4, maybe even 5 miles, but then you'll start seeing signals, somewhere in the -70 range or low to mid -70. So that may or may not be sufficient for you, but again, you can make up for that by using a larger CPE. So the answer is the suggested distance for a 90-degree antenna is like 2 to 3 miles.
Great, and then are there any plans for a 2.5 gigahertz?
2.5, probably not. I'm not going to say no. These antennas, all antennas, right? Size is kind of in, direct relation to the wavelength of the signal, right? So if you look at a horn antenna right now in 5 gig, you can imagine that a 2.4 or a 2.5 gig horn antenna would be twice the size. And actually, twice the size, physical size of a 5 gig horn antenna is not that bad, but the aperture, right, the part in the back where the twist port goes doubles in size as well. So really, I think anything below, 3.5 gig is probably not best suited from a form factor standpoint for a horn antenna. We are considering and looking at 3.65 or 3.5. So I think 3.5 and above, you might see some more horn antennas come from us, but below that, maybe not.
Okay, that's all I have as of right now. So if there's nothing else, Tassos, I'd just like to let everyone know that this webinar has been recorded, so we will have this sent to everybody that's attended to view, and then any other questions that came through, we will go ahead and answer them, and then we'll link it to the email that we'll send out either sometime later today or tomorrow.
Great. Well, thank you, everybody. Again, if you have any questions, reach out to us on social media or a forum. We'd be happy to talk to you direct. Thanks.
Bye.
Bye.